Yeah, exactly. So, as you may notice or not, I didn't go so far as I was expected. I mean, really not so far. I mean, like everybody, but I mean, I was really so stressed. So I will still continue the same plan. I mean, like, and eventually we see where we end up at the end of the 4 lecture. But I do apologize eventually for people who know better. But I mean, from the exercise session, I realized that, yeah, I was not going too fast, obviously, at least for some of you. And eventually I will not reach so much advanced subjects at the end of the talk, but I think that's fine. So I will continue and not skip like, okay, forget yesterday, the proof is a theorem. So I will continue to prove the theorem of yesterday. That's basically what I'm going to do, even if I was supposed to do it yesterday. Let me recall the situation, not the statement of the theorem, but what was the main object I was defining yesterday. So I had something like this. I defined to be, I wanted to think of it as a tensor product of some chain complex of bimodule over Rk. Let me put the shift properly. I mean, it's annoying to take care of all grades. At the same time, if you take some time trying to do this, it does really help a lot, telling you what the map are or what they look like, because actually there's no flexibility. So this is in degree 0, and this is in degree 1, and this map is just sending, if you recall, 1 to 1. And then there was another functor or under-functor, which was supposed to be an auto-equivalence of the category, which goes the other way around, which goes from Rk into Bi into 0. And here, sorry, I goes from 1 to k minus 1. So I'm looking for the braid group on k strand. So this is this k, what is remembering this k. And then you have a shift here. And here I put this in degree 0, and I put this in degree minus 1, sorry, and 0. And this map is slightly different. So I propose various ways to think of Bi. So using this prime variable or using the usual more Bose-Samuelson version of this Bi. Let me just recall what Bi is. So Bi was something like, let me do it like this for the moment because it's slightly quicker. And I had a convention that I shift down this q minus 1 as well. So this is, recall that Rk was just z of x1, xk, and these are the polynomial in x1, xk, which are symmetric in the variable I and I plus 1. So the invariant part under the transposition, so Si is meant to be transposition of I plus 1 acting on the variables. And this map sitting, giving it again in a different way, this map is sending a 1 to probably, what did I do yesterday? Xi tensor 1 minus 1 tensor Xi plus 1. So there's no prime, yes? Of bimodules. This is a bimodule map. So this module is generated by 1 as a bimodule. So you just have to specify where 1 goes. And here I mean, if you prefer here, it's a 1 tensor. Sorry? Yes, with the left action of Rk. If you recall yesterday using this prime and non-prime variable, I was just saying that Rk is a quotient of Rk hat by defining the action on the left and on the right. All good so far? So I noticed yesterday that, so what I want to prove, what this theorem requires to prove are two things. So one thing is this. And what this means, this is an underfunctor, another underfunctor, and composed underfunctor. So it will be equivalent to the underfunctor 1, to the identity underfunctor. So this equivalency is they are natural transformation between this and this with the natural condition. I was somehow expecting that people would know that. Apparently, not everybody does. So let me rephrase this in a more proper way, which is very specific, that these functors are not just random functors. They are tensor products with an explicitly given complex of bimodules. So this amounts to say, in this case, that if I take the tensor, give me name, hoping that it will help some of you. Let me give a name to this complex. F of sigma I, usually you find it in the literature, and eventually F of sigma I inverse. So this is just the complex. So between the complex and the functor obtained by tensoring with this by this complex. So this is exactly the same. So this is equivalent to say that F of sigma I tensor over Rk of F of sigma I inverse is homotopy equivalent. Sorry, let me say is homotopy equivalent to what should be 1 as a functor. So I said yesterday, but let me rephrase it, to the complex 0 Rk 0 sitting in common degree 0. I mean, this is just exactly the same statement. Okay, and then I started to do that yesterday, and I will continue to do so. But let me just say immediately what's also left to check is F of sigma I tensor F of sigma I plus 1, tensor F of sigma I is again homotopy equivalent to F of sigma I plus 1, tensor product F of sigma I for sigma plus 1, and all the tensor products here are over Rk. And this here is, so that's from the context, this is the homotopy equivalence of complex of bimodule. So far, so good? Let me recall, yes? Correct. But let me just check only one of them because it's just obvious from symmetry that if one of them is true, the other one. But you're right. Thank you. So far, so good. Let me recall one exercise or lemma I left yesterday. So recall, I don't know if you did the exercise, but let's pretend you did. So what I left yesterday, again, there's various ways to written this with all the notation I introduced yesterday. So there is such a short equal sequence. This is a split. There exists a short exact sequence split. So a split short sequence of bimodules. For me, all bimodules will be over Rk, and let me not specify the map because that's an interesting exercise I really suggest you do if you didn't. Now just tell me what the first map is. So the first map is just one. So let me say Bi is here. So Bi, you can always say an element of Bi. What's an element of Bi is as a bimodule is generated by one tensor 1 with the left and the right constant. So as a bimodule is just generated by one tensor 1. So if I tell you where one tensor 1 goes, then I'm good. And you just send this to one tensor 1. And again, what is Bi tensor Rk tensor Bi? So Bi over Rk of Bi, this is the same as Rk tensor Rk, and again over each over the symmetric polynomial in S variable. I make priori you make an identification which is Rk tensor Rk over Rk is just Rk. So you don't need that. if you play with a set of variables, I'm just saying if you have a set of variables for bi on the left and on the right, and you tensor with another bi, which is another set of variables on the left and the right, I just identify the variable from the right with the left ones, which is amount to say that you collapse this rk tensor rk over rk. This is just all the same things, just a slightly different way to say it. Okay, fine. And or maybe let me do the exercise. I mean, part of the exercise. To do so, what you have to check is that the right. I mean, check various things, but in particular, you need to see that if I tell you I'll send one tensor 1 to 0, and one tensor xi tensor 1 to 1 tensor 1, this is a well-defined bimodule map. Is the image of the other one. And there's a section. So this is, I want to say that this is the one in the middle is just a direct summand of q minus 1 bi, direct summand with q of bi. So far, so good? Okay, but recall that what we would like to do is to understand the tensor product of these two complexes. So let me try to show how this complex looks like. So I'm taking the tensor product of this two-length two-chain complex, which looks like, let me try to be precise for a while. This is rk tensor bi over rk goes to bi tensor bi goes to rk tensor rk over rk and goes to rk tensor bi, and to adjust all the shifts, which are probably q minus 1, no, sorry, q. And q minus 1, and let me add a small comment here because, sorry, I'm doing this tensor that. And this, you say I made it in the wrong way. Sorry, you're right. Okay, let me make a small comment because this was a long issue in Khovanov paper at the beginning. Here you are just tensoring complexes. So if you know how to do that, there's a sign that's spit out to make it a chain complex. Because if you look to the so what is the composite of this map? So let me recall also here, sorry. I was calling this unzip and this zip. I hope you remember the picture I did on the board yesterday. So this is just zip tensor identity. This is identity tensor unzip, and the other way around. So the composites as such is just this way. This morphism is just equal to that one. But of course, this is not the rule you give yourself to tensor product of complexes. So let me say that you have a minus here somewhere, and you can put it. I say that because in the original Khovanov paper using this cube of resolution, there was a large amount saying that you can choose a sign on this complex, and it's working well. And at the end of the day, actually, it's just the sign of the tensor product of complexes. I mean, there's nothing special about that. It's not because you have a hypercube. It's just because you're tensoring complexes, and the sign is. There's various choice of convention for the tensor product of complexes, and you just pick one. Very good. Very good. Yes? Yep, it does. So that's, again, let's put the degree. This is 0, this is minus 1, this is 1. And what you want to prove is basically that this complex is just this piece. Recall that this is just Rk, and this is what we want to prove. So this means that you can remove, up to a motor P, you can remove all this part. Okay. So there's, I mean, you can do it in various ways. And like in my origin plan, I wanted to do in a specific way, which will be compatible with what will eventually come at the end of the Fourier lecture. So let me continue to do so. But in this case, you can explicitly make a chain homotopy, as Liam was doing in the Khovanov complex. I mean, you can explicitly give a map from this complex to the one which is concentrated in degree 0 and 0, and do everything completely explicitly. I will take a slightly different view, which is using a short extra sequence. So removing contractual summand. So which is, again, just a way of rephrasing things. So let me do it using this short extra sequence. So what I want to put here is Q minus 1 BI. And let me use color to notice morphism which are again, and so the blue arrow will mean identity, always. This is an identity morphism. Q1 and BI. This is also an identity. I mean, but I abuse slightly notation because I make immediate identification of RK tensor BI over RK is just BI. So this is just BI, this is just BI. And then the map which is here is just the map you define here. Okay, I'm just putting this arrow here. Okay, I know I'm taking the image with a quotient. So what's left? You have BI here, to be precise, Q BI. And this is RK. Maybe if I make it higher. And this is now Q BI. Okay. And what are the arrows? So this is just an identity. Again, I'm putting it into blue. This is again just an identity. And what's missing, because this is not even a chain map, so you need to pick a piece which goes here, from here to here. And what is this arrow is just that one. Okay. And the claim is that this is a short. This is a split short exact sequence of complexes of bimodules. Okay. The fact that it's a short sequence is immediate if you have this. The only thing you have to just take attention a little bit is that the composite, what is not completely obvious is that the composite with this map, with the green one, will be just that one. I mean, you have to check that it's a chain complex map. And for all the rest, it's almost immediate. And then what you have to check is that it's split. So there's a section of all of that. So what remains to say is that this piece is contractible. Okay, you can just erase because this is just the identity. So there's nothing left. There's no homology here to compute anyway. So this, at the end of the day, what this short sequence tell you is that this, the complex you care about is homotopy equivalent to the one which is smaller. And what I did, I removed the contractible piece out of that. And this is how most proofs do work. You remove contractible pieces that you have to identify and understand where they are and how they behave. Everything so good? So I'm not completely done, then I just have to tell you.
So once again, this thing,
Yes.
you find a contractible subthing.
Yes.
I can take the quotient.
Yes.
But do I need to know that it's a direct summand?
Yeah. No, you don't need to, a priori. That's, okay, let me precise. That's depending on how you want the statement. If you want it as a complex of bimodule, yes, you need to know that you can just eliminate it. So it's a.
It's almost a different question when you use the exact sequence.
You really need the section. You need this to be a direct summand of that one and that one.
Even if I work in this homology.
Yes, you do. Because what you can do is that if you what's formally was something which is called by Barnard the Gaussian elimination lemma. I don't know if you aim to talk about that, Yam? About Gaussian elimination? Okay. Okay. So the point, what you can do is that you can do slightly better than what I just said, is that if you see a piece of a morphism which is an isomorphism, so if you have this as a direct summand, and then you see just this isomorphism, then you can remove it. But again, it's homotopy equivalent to remove it, because and what is true, because you can find such a statistical sequence which does split, and for which you can remove it. So you really need to have the section, so it does split, and you have it. I mean, I'm just not telling you how to do it because I think it's worth doing it yourself. Because again, everything is explicit, and you have no choice actually. I mean, it's like I'm searching you for a section. I mean, there is one, and if you look to degrees, and you will guess what the map is yourself. I mean, there's no difficulty in that. And let me finish by maybe let me finish the proof. Let me consider again the one on the bottom, and maybe this will help you, Gregor. So, looking again to the bottom one. So in this case, what you want to prove is what's left is that you put RK here, then you can prove that, and 0, sorry, here maybe. I didn't put the 0. Okay, is that okay? If I didn't put anything, then the map has 0 and everything is 0. Again, and this is identity. And now, this is also, you take here also as well the identity. And now, so this is a non-zip. Yes. And now you want at least a chain map which goes the other way around. So what you do if you do it this way, so let's put me, sorry, it's blue again. This as well as the identity, but no, this is not a chain map because if you go here and here, you're just doing an unzip from here to here, whereas whatever you're doing, it should be 0 because you pass by this is 0. So what choice do you have? Well, not that much. You just let me put it in green. This is also an unzip. So this is at least a chain map. This is another chain map, which just inject this copy into here. The composite this way and this way is obviously the identity, because you inject here and you do nothing. And now you do the composite the other way around. You do the composite the other way around, which is, sorry, you start here and you go down. So you see that in the composite of this map, you have someone who starts here, goes here, and goes down here. So this, you have to compensate this by an homotopy somewhere. And how you do that? I mean, this is just unzip identity. So what you do, well, you are not that complicated. And probably you put a minus. So that's minus identity. Homotopy. And so this is an explicit homotopy equivalence. We can remove this contractible summand, but what's different from the situation which is below, here I can clearly see an isomorphism showing up. I mean, and what I did just here is what Barnatan would call a Gaussian elimination. I did eliminate this arrow and the source and target, which are isomorphism. And you have a general argument for doing so. So this ends up the proof of sigma I inverse composed with I is homotopy equivalent to the identity. Okay. So I stopped doing picture for a moment, doing pure algebra. Okay, let me come back to pictures. More pictures. Because this is where we'll go, hopefully by the end of today. You remember this picture? I mean, I hope you do. Which was aimed to be a picture describing what BI was. I mean, variable xi plus 1 prime, non-prime, and this end to say this, you make an identification of this set of variables, but just over the symmetric polynomials in these two specific variables. Again, and now let me draw a picture and then tell you what bimodule it is. I will do a new picture. Okay, this is aimed to be a new picture. And this is aimed, again, to be a bimodule. So let me describe what it is. So this is, again, a picture for something I will denote bi I plus 1. So it does depend on I and I plus 1. It doesn't really depend, let me say it. So let me say it in words and then write it down. So you have three variables. Let's say x1, x2, x3, just to make it simple. x1, x2, x3. So eventually here you have another set of variables, and you're saying you're just identifying the symmetric polynomial here as a subset of variable x2, x3, and here the same. And then you continue. So what you do at the end of the day is saying, okay, I'm identifying the top variable and the bottom variable, but only when they are symmetric, fully symmetric in the variable x1, x2, and x3. So let me say it explicitly now. This is RK modified out by, with the same convention as yesterday, hopefully, xi prime, x1 plus prime, xi plus 2 prime, xi plus 1, xi plus 2. And what I was just saying is that what you require is that xi plus 1 plus xi plus 2 is equal to xi prime plus xi plus 1 prime plus xi plus 2 prime. Herke hat was a set of all variables. There's a bunch of variables. I'm abusing notation. Well, that's a good remark. You could do everything. You could do the previous proof completely in the case k equal 2. Because if you pick B1, B1 is what? Well, what's the part that does matter? Is that one. And all the rest are just basically tensoring over the z coefficient with the other variables. So the other variables never show up and never play any role in the proof I just done there. So you could do the proof for k equal 2 as well, and this will imply the proof for bi, the sigma I in full generality. And the same here. You could do the proof for variable for k equals 3 with a set of variables x1, x2, x2, x1, x2, x3, and this will do the job as well. then what you do, well, you do identify, sorry, x1 plus 1, xi plus 2, plus xi plus 1, xi plus 2 is equal to, but with the primes, so, okay. I mean, if I introduce slightly the notation, so this is what I would call E1 I in the X. Well, this is E1 I in the variable prime. Yes?
Sorry, this up, right, and also left. Because before we said left action was a right action.
Yes, so I'm using the same convention, so the left action is by prime and the right action is by non-prime in this simplification. And yes, and what's left is the other variable. Okay, and again, you could say this is the same as saying that E2i in the variable x is equal to E2i in the variable prime, and this is just E3. I in the variable x is equal to E3 in the variable x prime. Okay, very good. There's a shift that we need to take care, which is probably q minus 3, and give me again another description. So this is the same as RK tensor RK over the subgroup of the symmetric group in two variables generated by exchanging I and I plus 1 and I plus 2 and I plus 1 and I plus 2. So this is just a copy of S3 of the symmetric group in 3 letters. And again, you do a shift. Yes?
You could just define it. Can you give some intuition to why you think about this? Like the other bimodule where you intertwine using symmetric polynums.
Yes?
That feels like the right thing to do based on what you see with Hackett algebras.
Yes?
You preserve using symmetric representation that does this have the same intuition?
Yes, exactly. I mean, so, I mean, as I said, I didn't talk all about the non-Categorial word. So what Liam is pointing at is that what's behind everything I'm saying right now, there's an object which is called the Ecke algebra. So again, maybe you know what it is or you don't. If you do, so the Ecke algebra is a quotient of the braid group. So it's a finite dimensional algebra, which is a flat deformation of the algebra of the symmetric group. And this means that the representation theory of the Ecke algebra and of the symmetric group are the same. And this is another bimodule which plays a role, which is one of these Soergel bimodule, which you can play with to get a classification of the Ecke algebra itself. So let me say it. I mean, maybe I continue the proof. You will see. Yes. And the other thing that you may care if you want to understand the relationship between Khovanov homology and what Liam is saying and this picture, one important feature is that this guy precisely doesn't exist in the Khovanov setting. It disappears. And this for a representation theoretic point of view. But let me not say that. So this guy is the one which is causing trouble, moving from Khovanov to something which is related to a higher rank Lie algebra, and which is present here because somehow this Soergel story is taking care of everyone. Very good. Very good. So again, and what you eventually see from this picture is that I made a choice in the picture. But if you look to the algebraic definition and you want to understand that what matters in this picture, the fact that I was first embedding the variable I plus 1, I plus 2 as a symmetric polynomial 2 variable, and then so on and so forth, absolutely doesn't matter. So the picture will be the same. They will just mean the same bimodule, so it doesn't matter which one it is. So let me put the lemma. So let me put the lemma, and hopefully again with picture. So I'm using this picture, where one of them okay, very good. And then I'm going to, let's say this. So let me first comment. So the lemma, this is a split short sequence of bimodule. So this is a split short exact sequence of bimodule. So answering Liam, this means that even if you wouldn't know the existence of this guy, it does show up because you need to understand how this element that you may recognize as piece that will show up in the complex associated to the Yang-Baxter equation. So this is, it will show up in sigma I plus 1, sigma I. You need to understand this. If you try to understand the symmetry that you show up, you need to understand the default of this one with the reflected version. But let me say it like this. There's another short sequence when you reflect or the picture here. So there's another one. And now let me use the other picture. That's also a split short exact sequence. And you see that somehow this bimodule is like the symmetric part with respect to the reflection to that one. So if you are able, in some sense, to remove the non-symmetric part, which does depend upon which side of the world you are, then this one would be symmetric. And reflected by the fact I just noticed that this picture is just equal to that one. So it doesn't matter which one you use. It doesn't depend on which side of the Radmaster 3 moves you are. They are just the same. Let me just comment a bit on the morphism. I'm claiming that this morphism is obvious. So here you have RK hat with a set of variable here, a set of variable here. And if you write down what explicitly this is, it does identify, you need new variables for the one in the middle. So this first piece identifies the symmetric in the two variable with the one in the middle, and then the symmetric in the two last with the bottom, and so on and so forth. So what's clear is that this identification are in the kernel of the projection of RK into RK hat with all you added. That's fine. It does factorize by that. It's not subjective a priori because it's really most like the one which is just on the top. Fine. So what I'm saying is that whatever you define, this is 1 tensor 1 goes to, if you want to say it as the bimodule, this is 1 tensor 1 goes to 1 tensor 1. So with the 1 tensor 1, I mean this definition here. And by this, I mean bi tensor b plus 1 tensor bi collapsing all the things. So if you think of it, there are 4 factors. And that's a bimodule. I'm claiming this is a bimodule map. No problem with that. And now the question is what this map is. And this map is easily defined as a composite of 2 ones. So one of them is you just go there with just saying it here. You just unzip this one. So that's a morphism already defined. And now how you go from there to there, you need the complicated guy. So that's the green arrow, which is on the top of the shortest sequence. And yeah, and then you have to check that there's a section, and so meaning that this bimodule is a direct segment of this one and that one. And that's the key, yes? I mean that's the key. This lemma, what will be good to understand is that this lemma, these two shortest sequence, as was the case before for the R2, this is essentially the end of the proof of Ride-Master moves. I mean, of these two sentences I was asking before. This equivalence, homotopy equivalence of this chain complex, rather complicated, do follow from the fact that this specific bimodule splits this way and this way. Go ahead.
So I'm wondering if I want to check that this right analog is it too smart people. Is it the case that when you think about Khovanov-Rozansky's first paper about the homology,
Yes.
it's proof divided by 3 that depends on divided by 2, and he sees how it breaks.
Yes.
So introduces like a symmetric object.
Yes.
Cones.
Yes.
Is that the right thing to understand if you want to come back and see?
Yeah, but the point is that this piece, as I said, I mean, this piece doesn't exist in Barnator. Yes. Yeah, exactly. I mean, this piece is the same. I mean, this point is exactly the same as you did. But still, you have to deal with this one. This past, okay. Let me draw a picture. Let me show what the. I will do it in a second. So let me come back to Liam picture. So if you recall Liam picture or I mean that's my picture. I mean that's the picture I'm using, and this is Liam picture. Okay, and now you think a second about what's happening to this one and that one. And you do the picture. So this picture is just this. And this picture is just this. So this means you don't do this. In the Khovanov setting, whatever it is, this is just an isomorphism and this is 0. And just because you don't need it to control what's happening. Because, yes, it's just 0. Yeah, because you know that this picture is meant to represent an intertwiners in the UQSL2 representation theory, which means that this is the third exterior power of a representation which is dimension 2, and this is 0. Forget about it, we don't care about it. And I'm just saying that. All good? So the only thing I want to finish with that, I will just sketch, roughly speaking, how this, for one of the side of the Rasa 3 moves, how you use this sort of sequence, at least with pictures, how to cook up and remove condition, and I will let you check that what everything I'm saying is fine with it. Just to do a slightly more complicated chain complex. So well, I should have said that. Okay, let me continue to erase. Maybe no, let me keep that for a second. Okay, so how does So you tensor 3 lengths 2 complex. So this is a hypercube of dimension 3. In other words, it's a cube, which you may have seen with different flavors. No, sorry, making picture too big. I will not succeed. Okay, let's see. I did that. No. I changed mine in between. I changed my mind in between and what? And here, sorry. Okay, this is just, what did I do? This is just f of sigma I plus 1, tensor f of sigma I, tensor f of sigma I plus 1. And then again, I'm not careful with the signs of the differential, but all the map, if I do nothing, just do commute. So all the faces commute. So if you go this way until here and this way, they are just equal. So let me not do that because I will mess it up. You just put signs such that they do anti-commute. So this is a chain complex. Just because you have tensoring chain complex, and there's a sign rule for the tensor product of chain complex to make it, again, a chain complex. So meaning that chain complex is a monodial category. Is that fine for everyone? There are signs somewhere. Let me just ignore this question or work over F2 as most people did in somewhere. So fine. Let's see. Fine. Okay, let me put somewhere here. And since I have constructed this map, so this map is the one in the shortest sequence. Okay, the which is not on the board. Well, it's here. So that's the right-hand side map which does factorize by this map, which is just going here, right? So what you see is that if I put identity here, and I'm doing this, and I'm using here the green map, and as well here the green map. Since I define this map here just to be exactly go there and take the green map, and I'm just putting the green map, which is the one in the shortest sequence. So this is just a well-defined chain complex map. Okay. Is that fine, everybody? I mean, you go there and you do 0, and I mean, it's just a chain map. And what you see, of course, that I'm picking you a contractible cement again. And what's remaining? What would be remaining? What would be remaining is a piece which is here, which you do complete with the arrow of the shortest sequence. And as Liam was saying, I'm again using the fact that this element does decompose as direct summand of 2 copies of this precise element. So what's left a priori is something like, I hope it's not too small. So what I'm just saying is that this piece again does split. So if you want it into a shortest sequence, again you use the first shortest sequence I recall today, which I was using today, which injects this one into that one. Probably this was orange today. Okay, and let me not put all maps, but then you have still this copy of this one is this, and you just go with identity. So the map I'm not showing you are just identities map. And what is as well important is that you have to understand what the map do remain here. And the map that do remain here are just identity as well. So I'm not putting, because you will not see anything, because this goes identity here, identity here, identity here. All the rest is identity. And I'm claiming this is again a short exact sequence of complex of bimodule that does split. And you are removing this piece. Is that okay? And again, you have to check. I mean, I just ask a couple of things you check. You have to find the sections, so it does decompose. And because I'm already running out of time, let me say again that what you see here is an isomorphism between two pieces of the complex. So again, you can remove one contractible summand. Okay, you can still remove one of this because this is just identity, and you can remove it. If you do so, what remains is something which looks like something like this. No, sorry. If I remove this segment, I will only have one of this type and one of this type. These are the two guys which are here. The one I will keep as these two, and the one in the source. And what you can recognize in this picture is if you just follow the same process with the other one, then it's completely reflection invariant. So you get exactly the same complex reduction, which is a symmetric version of the once each side of the Rasmussen moves. And so the magic is that these are just the same. You have to check that all the maps you obtain are the same and everything is the same. But I hope this gives you a hint about, I mean, a glimpse of how the proof work in this kind of setting. End of the proof of this theorem of Fourier. Yep. Okay, so I have this Hilbert cube, which is hopefully here. And the first thing I did is that I got this map. And now I'm asking basically what's the kernel of this map. But I already know that this bimodule into this one can be put into a shorter sequence where I defined basically the kernel of this shorter sequence to be that picture. And again, this shorter sequence from here to here, that's one I was using yesterday. So this is also a kernel, and he has another copy of that one. And then for all the rest of the pictures, meaning that one, everything which is here and here, I'm just taking exactly the same. On the top, I'm putting identity such that it becomes a short sequence globally. Does it help? Any other questions? Okay, fine. More algebra. And more algebra means we do need something which is called Hochschild homology to get where we want to go, meaning this triply graded link.
So
Yes.
now we have proved this theorem.
Yes.
The theorem was that we have this break representation.
Exactly. And now if you know the classical story, basically what I get somewhere in the Heckel algebra, and now I need the trace of the Heckel algebra to recover the home fly polynomial. And if you don't, I'm just going to get it in this way. So I have an invariant. What I do have is an invariant of the braid, not of this closure. Now I do need an invariant of the closure. And for this, I'm going to use this the so-called Markov theorem. And yeah, is that okay? So a quick definition, nothing else, of Hochschild homology. So if B, let B be an RK bimodule, then, well, of RK with coefficient is B. So let me give a definition which is useful if you know derived tensor products, and if you don't, I'm going to give another definition in a second. So the quick definition, this is the Tor, what I want to say to it, star of R, B, okay. So how do you compute, let me say how you compute such a thing. So the first thing I should say is that here's a new star. So there's a new grading coming into the picture. Recall from yesterday that there's the grading coming from what's called quantum grading, so the grading of the polynomials. I had the grading of the chain complex I already showed you, so I'm missing, at least from the title, I'm missing a third grading. And this third grading will be given to us by these Hochschild gradings. So how do you compute that? So RK, RK hat. So I didn't say that yesterday, but RK hat is in particular isomorphic to RK over the RK opposite. Since RK is commutative, RK opposite is the same as RK. So this is sometimes called the enveloping algebra of RK. So what does this mean if you doesn't know what it means? So this is mean Tor I of RK hat of RK with coefficient in M. This is the homology, the ith homology of either C of RK tensor B, which is also isomorphic to Hi of RK tensor Ym become B because I change notation between my knots on the board. It's B everywhere. And C, B, fine, where what? Where CRK is a projective resolution of RK as RK at mod, and the same for CB. Okay, let me go into explicit things because that's non-explicit. Because you would have to know that this resolution does exist, if they are finite or not, and the answer is yes, they do exist, and they are finite because RK is nice. And let me give an explicit version of what this does mean exactly. This means so this is so-called causal resolution. In our case, it will be better than a projective resolution. It will be a free resolution. So meaning you're going to resolve RK by free RK hat model. And let me do it by example. And let's do the case k equal 1 for a second. So R1 is just z of x1. R1 hat is z of x1 prime. And so I want to resolve R1 with a free resolution of R1 module. And as I said yesterday, R1 is just a quotient of R1 hat by identifying the left and the right action. So it's saying just x1 is equal to x1 prime. So you can easily guess that, that this does the job. So that's a free, so I will define as an example of a CR1. So projective and in particular free resolution of R1 as a R1 hat. Well, yes. Yes, that's good. So there's a new degree. Yes, thank you. And I choose homology. So this is a 0 and this is a 1. Be careful, or I should change color. I put in red. So I'm using homology, and why I'm using homology? You could use cohomology in this particular case. So there's a version of, I don't want to do it, but there's a version of Hochschild cohomology, which is a derived Hom functor, which is X functor, so you can compute it the other way. It turns out that in this specific case for RK, it really doesn't matter because the cohomology is isomorphic to the homology, which is not true in general, but for this specific case, it's true. The reason I'm using homology is because homology has a nice property that we'll need in a second, which is natural, always true for homology, Hochschild homology, but is not true for Hochschild cohomology unless you are lucky and they do coincide with Hochschild homology. Okay, that's a k equal. Yeah. This is an injective map. Multiplying by into RK by x1 minus x1 prime is completely injective. You multiply by a polynomial. Nothing can happen to you. And the image is just mod out by x1 minus x1 prime. So, I mean, I'm pretending it's like, yes?
This still looks like X convention.
Like?
This looks like X, not 4. So what am I right now in this one? I must be getting a grading back.
This is. Yeah, it's fine if you're going to think about X, but okay, I will not fix this problem absolutely on the board. As I agree, so it doesn't matter if you take cohomology or homology, so it really doesn't matter. Okay, I'm slightly confused with that thing. And the additional thing I want to take care right now is I want to put a Q2 here. Because remember, this is a degree 2 with respect to the Q grading, and I want everything to respect the Q grading. So out of that, causal resolution, so this is for general K. For K, what you do, well, since, yes? Yes, yes, exactly. You multiply by a degree 2 polynomial, and I'm shifting up the source, so you're gonna be of degree 0 with the Q grading if I shift it this way. Choice of convention for shift and grading are my responsibility, and if you look to the literature, you will find randomly various definition and convention. So my advice for that is choose your convention and stick to it. No, as a degree 0 with respect to the Q grading. I want to, for me, the Q grading is internal to everything. Yes. No, so that's fine. I mean, please ask question because 3 grading is quite a lot. Fine. And so for general K, what do? You tensor something. This is something I said like not really, but I use it quite a lot. Fine, this is Q2, this is degree 0, this is degree 1. And just to be sure, this tensor product now is over Z. So that's a contribution for RK as a RK hat module. So meaning I'm claiming that I'm slightly abstraction. This is the map into RK, which is a surjection. If you look to the homology of this chain complex, what's in degree 0? In degree 0 is the quotient of Z of xi prime tensor with all of them over Z. So this means that this is RK hat, modded out by the image of the differential, so modded out by identify left and right action for all i's. What you notice, so a slight remark, which is kind of important. Hochschild homology of RKB, so RKI, is 0 if I is strictly greater than K. So there's a finite amount. This is a finite amount of Hochschild degree, which can be non-zero, just because this resolution with respect to the purple grading, so the Hochschild grading goes from 0 to K. If you tensor K times a length 2 complex, you could have worse this factor tensor for each of them living in degree K. You mean for this one? Just for him? Yes. There's a prime missing, I guess. Very good. So now a few properties. Sorry? Yes, it looks like, but I never thought about it. Well, we can discuss that later. I'm slightly confused, but my quick answer will be probably yes, but I would like to double check this statement. So let me again be completely explicit. So that's a resolution of RK as a RK hat module. So how do you compute what we care about, meaning this? What you do, you tensor with complex with B over RK hat. So meaning you identify the left and the right action. So in particular, let me say what's happening for HH0 of RK B. So what is just a 0? You tensor with this, and you identify and you take homology of this complex. So this means that you take the bimodule, and you identify the left and right action of xi and xi prime. So this is just B modded out by, let me say it like this, and usually written like this, RKB. So you identify left action and right action. let me say it again in another language. This is just if B, again, just recall that I was using this variable to help you. So I was calling the left action prime and the right action non-prime. So what you do here is just you identify the left variable with the right variable. This is what you do when you compute the homology for the degree 0 part. Okay? Let's do that with pictures. So you have your graph, whatever graph it is. Example with picture. Well, you should be identifying the left and the top action. I propose to do like this. Okay, I identify the left set of variables on the bottom with the right set of variables on the top. I'm saying they do act exactly as the same. And no, it's not an X. Whole. I want to record that this is somewhere living in an Andus. If you want to think topologically about what it is. It's not an X, thank you. So properties that I will suggest you check. That's a useful thing to do if you never played with Hochschild homology. Yes. Zero. Only zero. Yes. I mean, I'm just giving you a picture for HL0. I'm not giving you a picture for high Hochschild homology, which is more complicated to describe. And which by mean more complicated, I mean I'm going to use forms if you want to do so. I cannot play just with planar diagrams. I need to tell you more structural things. I mean, for today, it will be HS star. I do need for triply graded. Now, if you do care about Khovanov homology or other construction of this kind, you only need one single Hochschild degree, which will be zero in some cases, but for Khovanov homology, it will be HHK. To be see if you want me to anticipate about what's going on after. So if you want, so properties is this thing. So this Hochschild homology of a tensor product of do pi module B1 and B2 does have the trace property. So if you tensor them the other way around, again, B1 tensor B2 is not isomorphic to B2 tensor B1 as a bimodule. This is not true. You can quickly find an example which is this is absolutely not true. But what is true is that it has a Hochschild homology and all of them. What is obvious from this remark, this is obviously true. If you understand the pictures, this is obviously true for HA0. Because what will be in the picture world tensoring with the other way around, meaning that you're going to cut somehow your picture in the middle, you're going to put it the other way around, and then close it again. So it doesn't matter. This property is just true. And the claim or the classical fact about homology, this is true for all Hochschild degrees, not just for the 0, 1. And this will be useful for us in a second. And the other thing I didn't tell is that Hochschild is a functor. I don't want to expand too much on that, but you can. So it takes a Soergel it takes a RK bimodule and speed out what? So what's new is it's graded. So by graded, I mean there's a star here. I mean, it just only give you one single thing, but something which is graded by Z. And what is not completely clear at this point, and I don't want to expand, actually it does give you a RK module. So of course, since you identified the left and the right action, you killed any sort of bimodule structure. But I'm claiming what remains is something, and what remains is the RK module structure. And I don't want to take care. If you are not happy with the RK module structure, just say it's split out a graded abelian group. Okay, the Z action survives everywhere. So if you are not happy with the RK module structure, just think we have an abelian group. And this is completely clear from the whole construction that scalar will survive everywhere. And the claim, this is a functor. Meaning if you give me a bimodule map, it does induce a degree 0 graded RK module map or abelian map if you want. And we do care about that. Yes? Yes. I mean, if you want it, each of them is a functor in non-graded RK module, and they are organized in a graded one. No. Yes. It's specific to RK, I think. It's because it's commutative, and it's cause you. I mean, it's nice in a very Tarzan way. Is it true? No, I think it's fine. We can list. I mean, you had a doubt about the fact that you have an RK module structure. You doubt about the RK module structure in general. I mean, I agree it's not true for any ring or algebra you take. That's definitely not true. I'm just saying it's true for RK. And you don't need to take the subset of bimodules. I do care. It's true for general bimodules, I think. I think so, but I can double check. But fine. Finally, I will define triply graded. What triply graded link homology is. Ready? Definition. So if beta is a braid, HH of, let's say, of beta. Okay, let's recap what we did. So so far, we associate to a braid a complex of bimodules. This is the theorem of proof today. So I gave a name to this complex, which is f of beta. So this is, you give me a word presentation of beta, sigma 1, sigma 2, blah, blah, blah. And f of beta is just a tensor product of the f of sigma. And it's well defined because we checked today that is well defined. OK? So that's a complex of bimodules. OK. Since Hochschild homology is a functor, I can apply Hochschild homology to this complex of bimodule. Let's do that. So the first thing, I'm taking all the bimodules showing up, and I'm computing Hochschild homology of each single bimodule showing up in this huge complex. But since Hochschild homology is a functor, and you add a complex of bimodules, still got a complex of RK module or the abelian group or graded and everything fine. So you can still compute. Oh, sorry. You're right. Well, this is a slight abuse of notation, but let's do it like this. Okay. Blah, blah, blah. See, so this means, again, this is meaning I'm applying a Hochschild homology to the chains of F beta as RK bimodule. All good? But what is this? Once you have done that, this is still a complex of, let's say, RK module. Okay, with something I will call dt star. So dt was, and dt, let me say it in word, dt was the differential on before taking Hochschild homology. These are the piece of bimodule maps I was playing around. But these bimodule maps on this hypercube, if you look to it, do induce module maps. And this is what I call dt star. And so this is a chain, this is still a chain complex, and I'm taking homology of it. Okay, let's count gradings. One grading is for Hochschild grading. One grading is internal, so this is quantum grading. This is whatever these Q are playing around. And then there's this chain complex grading. So I have 3 gradings. And then the dt is, so F beta is, let's say it like this, it's a C with a dt. So it's a complex of bimodule, and I'm calling this differential of this complex of bimodule just for a second dt. This is the arrow I was playing around all the day. So F beta is, so this is a complex of bimodule. And dt star is X star? Yes. With obvious notation. Okay. Go. Yes.
So in the definition, you have CRK tensor B. So CRK comes from the differential that gives that one the solution. B has its own differential. And what I would do when one takes the homology,
That's a wonderful remark.
you are doing something else.
No, I'm doing something else, and that's something I learned from. I mean, so what Paolo is saying is that, let me rewrite this again in a slightly different way, making transparent. So I'm just using different notation just to explain what Paolo is saying. I hope the way I did understand he was saying things. No, this is not H of CK or CRK tensor. Blah. Okay, the way I compute Hochschild homology is using this causal resolution. And let me call for a second this differential of this of each piece, the causal differential. So once you have resolved each bimodule using the causal resolution, what you do have, in reality, is a bicomplex with 2 differentials. One of them is causal, the other one is the induced maps given by the bimodule maps. So this is a priori a bicomplex at this stage. And what people do usually in this case is not what's written here, which will be, if you are familiar with the second page of a given spectral sequence, but they compute the total homology of this bicomplex. And this is what you would like to do. And we are not doing that. And somehow, to my knowledge, there's no good explanation why this would ever working. If you ask physicists, people, what would be naturally an invariant is what you suggest. If I take the total homology, then you're fine, you get a link invariant. For reason I cannot explain, and I would probably never understood, but you don't do that, and if you do that, it's trivial. It's not interesting. It's really, really not interesting. Yes? That's a good point, but which points to another remark. So yes, it does a priori give S-type invariants if you could live with general diagrams. So let me do my 2 rules for today. Give a theorem and give an open question. A theorem and an open question. What you say, Paolo, will be very, very true and very, very interesting and very, very useful if you, let me start with the theorem. Which is originally due to Khovanov-Rozansky. Up to shift H of beta is a link invariant. Well, of course, let me precise of beta hat. So at the end of the day, H doesn't depend on beta, it does only depend on the closure of beta. But of course, once you have done this, let me usually write this. So notation, maybe I will use it, is beta hat. Okay, it doesn't depend on the braid, it does only depend on the closures. And for this, you have to prove 2 things. I will come back to this. No. If you want to recover things in a natural convention of normalization of the polynomial invariant you care, you would like. But if you don't need to do variable substitution.
So this lands on their convention.
Yes, up to shift is around. Okay, so let me precise. Up to shift means, how do you prove this theorem? You prove that it's invariant on the conjugation. This thus follows almost immediately from the Hochschild property. And then you have to prove stabilization and destabilization, which amounts to say you have proved a version of Ramaster 1. Okay, there's a couple of things I want to say now due to all your marks. So the shift, first remark, the shift is made because Ramaster 1 will speed out shift in A, Q, and in all degrees. So you have to correct that to make it. So that's one thing. So it's not a big deal. It's just yes, up to shift in Q, T, and I didn't say anything, but let me say A degree. So that's Q degree, internal, that's complex, so that's and that's Hochschild degree. And that's sometimes I call it the topological degree or the complex. Okay. Okay, and eventually you have to shift in one way or the other, and you have to.
So the complex degree was what you did earlier today.
Yes, yeah, exactly. It was the T. This is what I depend sometimes. Yes. The T is the capital T. Yeah. Now, open question. And I should say that I'm putting open question just that people don't spend some time. I'm putting open question which I do think are very, very interesting open question, but they are by no means easy. Okay, it's like, so some of them in particular for that one I'm going to put on the board. I did personally spend some time trying to do it, and I'm just encourage you to do so because there are most people interested in the answer of this kind of answer, but there are already some large or pretty large amount of researchers trying to solve this question. So you need an idea, you need something. I mean, it's not like going on, but I do think it's important. So what I did so now is that I define a link invariant. So this theorem gives you a link invariant, which is, for the moment, only defined for break closures. Okay? And the point is that there's no definition. I mean, I shouldn't say that. There's a definition which is valid for general diagrams, so diagrams which are not in the break closure position. This was originally done by Khovanov-Rozansky by something which is called matrix factorization. But what's amazing, or disturbing, up to you, is that the definition, so they have a definition, but it's not invariant of general diagram. So it does depend on, if you know the difference between break closures and general diagram, what's important is that for general diagram, you need to check this bad or reverse orientation, red master 2. So they have a definition for general diagram, but it doesn't satisfy this move. It's just not true. It's not valid. But it will be for the total homology. Then it will be valid. It will be true. So open question, final definition. Of triply graded. For general diagram. By this I mean diagrams which are not break closures of break closure type. And you give me a definition. Huh? Yeah, but to compute it, you have to define it.
Yeah, but I mean, just to make sure, this is small.
Yes.
It does not depend on how I write something as a break. It's an invariant of orient.
But what is not known is you give me a general diagram and give me a procedure that associates to this general diagram a complex of bimodule or something, which computes the triply graded, which will be valid for break closure, which will coincide with this construction for break closure, but at the same time will be invariant in particular between this move. Because what I do so far is you give me a general diagram, I apply Alexander theorem, I present the diagram as a break closure, I compute the thing, and the theorem guarantees that this quantity doesn't depend on whatever I did before. But this is not something we would like. You would like to understand that you can do it directly on diagram, and the reason you care about is exactly for this S invariant section. So long as you have only S, so a break closure, you lose the topology of, typically the topology of the embedded surface you allow to cap off the diagram. So, I mean, even if there's an S invariant appear in this picture, how do you use it? You cannot, because you have not enough cobordism to play with in this rigid break closure situation to tell topology. Yes.
So if you have a surface, you can push the surface by this isotropy and it's still a different
Okay, I think I'm happy to answer, but let me just stop here and ask a question.